Hello, science students, and welcome to the States of Matter lecture for your alternative learning day. So, in this talk of sorts, we're going to look at some of the etymologies and definitions for different words that we might be using. We'll look at atomic structure and how to decode or make understood periodic table of elements and talk a little bit more about charges. And then we'll go into a refresher for all of the states of matter that we've looked at in class, just consolidating a little bit of that information together. So, moving forward, we have matter as the first word that we are defining. So, it technically comes from two words. So, mater and meaning mother, right? And this is about a discourse, like we're discussing the matter at hand. But we're looking from matter via Old French from Latin materia, which again, similar, is timber or substance. And we're really looking at substance. So, in a scientific definition, matter is anything that takes up space and can be weighed. So, if we think about the gases that are filling up a room, right? The room is a certain size, and we know that there's gases there if we can breathe in, right? We know that there's at least some oxygen that's allowing us to live, and it's taking up the space of the room. And if it's made up of atoms, even though we can't see them, we know that atoms weigh something. So the gases, even though they are high energy and they're free flowing, they have volume and they have a mass. They take up space and they weigh something. We're looking at the word state, which can often be used interchangeably with phase. But phase comes from um, the stem of stade, or the root of stade, which means to stand, with this little suffix at the end called, which is tus. So status. So from Latin, a status is the condition of standing, being um, stature, what something is like as we give it attention or as it's standing at attention, right? So state is a particular condition that something or someone is in at a specific time. So if you're listening to this or watching this in the morning, you might consider the fact that we can be groggy in the morning and you might be groggy yourself. And eventually, as the day goes on, you might get more energy. You actually might need more sleep and you might take a nap. So, if we looked at you at a specific time throughout the day, you're going to be in different states. Some of you are fully caffeinated when you're watching this, and you are absolutely at attention and you are taking everything in and you are ready to go. Um, these are different types of states at the same time, right? And both of them can change over time. Phase is a little bit different, and it has a very specific term in science. So, phase comes from the Greek phasis and phainin, phainin, and basically it means to show or to appear. So, as something appears to us. And in science, a phase is a region of material that is chemically uniform, physically distinct, and often mechanically separable. So, let us break this down just a little bit. So if we take this glass of ice water, and for the sake of just elucidating some concepts, we are not going to think about the glass, and we're only going to think about the liquid and solid water that is inside the glass. And we're going to call that a system. So this is a very simple system made up of liquid water and solid water. It's pretty cold. And so if we go back to our definition, chemically uniform, right? So if we took a region of this material, say we took this cube of ice, right? It has a volume, there's a region of it. And we think about what makes up the ice. Well, we know that ice is just frozen H2O, frozen water. So it's chemically uniform, right? It might have some other dissolved substances inside of it, but by and large, it's just frozen water, H2O, chemically uniform all the way through and through. Water, water, water. It is physically distinct, right? So if we take this cube here, it is physically different from the water that is surrounding it, right? So if we take that region, which is frozen water, we can say that it is physically distinct. It's in a different phase than the water, right? Or the liquid water. And so we can say that this system here, this simple system of ice water, is a two-phase system comprised of solid water and liquid water. And finally, a phase is something that is often mechanically separable. And this is where you can just imagine having a cup of ice water and you can reach your hand directly inside the cup and you can pull out the ice. You can literally separate the two phases from each other, right? They're able to be mechanically separated. We can take our hand, do some mechanical work, and pull out the ice cube. Finally, just for some good measure, we got the word change. Change comes from Old French to Latin, or from to Middle English from Latin and French, meaning to barter, cambiare from Latin, probably of Celtic origin. And barter essentially means to change, exchange, right? So when I go to the store, I take my money and I technically am like bartering for all of the goods that I am buying. So if I want to buy some Tic Tacs, I go take my dollar, I trade in my dollar for a Tic Tac. Suddenly, things have changed, right? The value of that dollar is now realized in the value of that Tic Tac. So I gave a dollar, I get my Tic Tacs, and something is different, right? Something has been modified. And so change is to make something or someone different, to alter or modify. Pretty straightforward, right? So if we keep going, we're going to see the structure of an atom. We looked at this in class. It's pretty straightforward. And we're going to start with the nucleus. So as we know, there are three particles that we think of when we're looking at the structure of an atom. And some of them are charged and some of them aren't. If we look at this, the way that this is represented, protons are red here. And we know that protons have a positive charge. And we can remember that because proton is positive, pp, right? The way that neutrons are represented here is they are blue. So a neutron is blue, and these two particles make up the nucleus, protons and neutrons. And neutrons don't have a charge. Neutrons are neutral, right? They are not positive, they are not negative. Neutrons are neutral. And finally, orbiting the nucleus is our electrons, which have a negative charge. So this is a very, and I've made this caveat in class, this is a very simplistic model, right? This is a very flat idea of what an atom is. There are more complex representations of what an atom is, and as we learn a little bit more, we might be able to go into that. Electron clouds and orbital shells and whatnot. Before we move on, say, just looking at this, we have a atom that has 5 protons in it, and we have our electrons, and say that we only have 3 of these electrons. So if we canceled out, if we went in and remember, positive and negative charges cancel each other out. So one positive is canceled by one negative and vice versa. So if we have 5 positives and 3 negatives, then we can cancel out 3 of the positives and we're left over with 2 positives, right? So 5 minus 3 is 2, and what's left over are 2 protons. So we have an atom that is positively charged. It has a net positive charge. All right, so let's understand the elements on the periodic table. So we may have seen periodic tables. It is a very specific chart that has a bunch of these little tiles on it that tell us a bit of information about each element, right? And an element is an atom that has a very specific amount of protons in them. So let's go through this tile really quickly. So these are the four most common things. You might find that some periodic tables will have more information on them, but in general, these four lines, these four sections on this tile are going to be found in every single periodic table. So we have the name. So for this element, it's cobalt. In cobalt, this is the name. In cobalt, there are 27 protons and 27 electrons. We represent this, the way that it's represented is a neutral atom of cobalt, right? So we have 27 positive particles and 27 negative particles that create a neutral cobalt atom. But it has 27 protons and 27 electrons. And the way that you change, say, from cobalt, which has 27 protons, to nickel is you add a proton to the nucleus. So you can take away or add neutrons in the nucleus, these blue things here in this representation. You can take away and add neutrons, and as long as you have 27 positive protons, it stays cobalt. But if you change the amount of protons, say we add one more, 28, suddenly we have a whole new element, and it is called nickel. So we have the name of our element, we have the atomic number, which is also the amount of protons in the nucleus and electrons orbiting, and then we have our abbreviation or our atomic symbol. So C, capital C, lowercase o. If this lowercase o was gone and we only had the capital C, this would actually just be carbon. So carbon has an atomic number of 6, and we know that whenever we just see a C by itself, right, without a small letter next to it, we know that we're talking about carbon. If we have a C and a small O next to it, we know that we're talking about cobalt, right? So this is the abbreviation or the atomic symbol, right, for cobalt. If we're writing something like H2O for water, we know that the H is hydrogen and we know that the O is oxygen because those are the atomic symbols for hydrogen and oxygen. And finally, we have the atomic weight. So for cobalt, it is 58.93, and that's literally how much the average weight of the most abundant kinds of cobalt there are in the world. So, like I said, sometimes cobalt, while it always has 27 protons, it might have more or less neutrons in its nucleus, which means it's going to have more or less weight to it. And so there are things called isotopes. So we looked at ions, and now we're going to look at isotopes. So an isotope is versions of an atom with different number of neutrons. You can have less neutrons than you have protons, or you can have more neutrons, or you can have the same amount, right? But out of all of the cobalt in the world, the different isotopes with different weights in their nucleus, this is the average amount of atomic weight that is in each cobalt atom, or in all the cobalts in the world, this is the average amount of weight that cobalt has. So say I had 27, cobalt has 27 protons. Say I also had 27 neutrons. Then I add 27 and 27 to get 54. And so my isotope is cobalt 54. It's neutral. Or cobalt 54 is just the same amount of neutrons and protons. If I had 2 more neutrons, then I add 2 more to 54, so 27 plus 29, and I suddenly have cobalt 56, all right? And so It's literally counting the amount of particles that are inside the nucleus of an element. And then again, if we go back to this guy, an ion is any particle that is charged, that has a charge, net charge, right? Because we know that protons are charged, and we know that electrons are charged. But since we have 5 protons here and 3 electrons orbiting on the outside, the 3 electrons are going to cancel out 3 protons, and we're going to have 2 protons that are positive left over, which means that this atom altogether is a positive ion, right? Because it has a net positive charge after the electrons and protons cancel each other out. We have 2 positively charged particles left over, which means it is a positive ion. So an ion is a particle with a charge, whether it's positive or negative. And an isotope is versions of an atom or species of an atom with different neutrons, number of neutrons. They can be less and they can be more. Generally, they're going to have more. All right, so we are looking at compounds. So an element is one single atom, right, that has a specific number of protons in them. A compound is any substance that is identical to itself. So let's take water, for example. This is a compound because we can have a substance that we can have a glass of water, which is a substance of identical molecules. The water is filled with H2O and maybe some dissolved solids. And then we can see that it is also consisting of 2 or more chemical elements, right? So we have 2 hydrogen atoms. Oop, it's a hint for what's coming next. And 1 oxygen atom, right? So we know that there's at least 1 hydrogen atom and at least 1 oxygen atom. So let's try to decode H2O. So H, 1H, this 2, and this O. Is it 2O, right? Do we think this is correct? Is there 1H and 2 oxygens? H2O? No, wrong. if you've never looked at formulas, this little number here is called a subscript, and this subscript applies to what comes just before it. So the O comes after this subscript number, and this H comes before it. So this 2 applies to our H. So this is really what we're looking for. We're looking for 2 H's and 1 O. And here we have it. 2 H's and 1 O. And this is representing the bonds that are holding these guys together. And so again, this is another representation. So we have our 1O here and our 2 hydrogens, our oxygen and our 2 hydrogens. And I just want us to pay attention really quickly to the bent shape. That'll be a little bit more useful to us as we move on and talk about crystals and ice in our solid portion. But we have a bent structure. There's some geometry to all of this. So it's at 104.45 degrees. It's not straight, right? It's bent at this angle. And again, water is a compound of oxygen and hydrogen. It has 2 or more chemical elements in it. If I just had oxygen, O2, because it's usually found in pairs, O2 is not a compound. It's just, it's a substance, but it has only 1 chemical element in it. But water has 2. At least it needs to have at least 2. All right, so let's go into our states of matter. So we're going to start with the lowest energy state of matter, Bose-Einstein condensate. And remember, the Bose-Einstein condensate was first theorized in the beginning of the 20th century by 2 scientists, Bose from India and Einstein from Germany. We may have heard of Einstein, but Bose is a really renowned Indian scientist that has made a lot of contributions to physics. And they theorized this in the 20th century, and it wasn't until, I believe, the late 90s that they this state of matter was experimentally confirmed. Like, they made this in a lab and they had sensors that gave us this data, right? This graph here. And so Bose-Einstein condensate, when we talk about having zero energy, we mean that it's really cold, right? So when something has less energy, when atoms have less energy, they are colder. If an atom has more energy, they're moving with more speed, right? They're literally moving faster and they have more energy and more heat. So, and again, that depends on pressure and temperature. But condensed matter becomes a wave function. So remember, particles, right, individual atoms are cooled down really, really cold, near absolute zero. And then they start to, instead of acting like grains of sand, they act like guitar swings, moving in waves. And eventually, as you get colder and colder and colder, so close to absolute zero, but not actually getting there, all that matter condenses together. All those particles condense together and become one giant wave. And so that's what we're seeing here is as things are condensing, we're getting a bigger and bigger wave function. And when we get a bigger wave function, you have these particles coming together and condensing. Things that are really small, quantum properties, are apparent more macroscopically. So things we would only see at sort of like subatomic levels below the atom, we can kind of see them on larger scales. Still not with our naked eye, but we can still see them. So, just before we move on, I did want to talk about scales really quickly. So, things happen, right? Water boils, our bodies are a certain temperature, water freezes, and there is a floor to all of this. So, when we want to describe when these things happen, we can think of it sort of as different languages for describing the same thing. I can say the word water in 3 different languages. So in English, it's water. In Spanish, it's agua. And in French, it's eau. So we have these 3 different scales, which are like 3 different languages, for talking about the same kinds of things that happen. Celsius is really nice, and we don't necessarily use Celsius in our everyday life. The rest of the world does. We use Fahrenheit, but Celsius is really nice because it's tuned to the point at which water freezes, which is 0 degrees Celsius, and the point at which water boils, which is 100 degrees Celsius. In Fahrenheit, right, in Fahrenheit, water boils at 212 degrees. So it's a pretty big change in terms of the actual number that gets applied to when water boils at normal atmospheric pressure. Water freezes in Fahrenheit at 32 degrees, right? So it's a little less intuitive in terms of when water boils. But in terms of the being able to have more numbers means that um, we get a finer texture on how to describe things like our body temperature, as well as our day and what it feels like outside when it's 85 versus 89 degrees, right? There's a little bit more numbers to give us more variety. And then we have our Kelvin, which there is a lowest temperature that you can go. So you can't get colder than absolute zero. And Kelvin is scaled to absolute zero. So 0 in Kelvin is the lowest temperature that you can go. And you can't actually get to absolute zero, but we know that theoretically this is the floor, right? In Celsius, right, in centigrade, there is negative 273.15 degrees Celsius is the lowest temperature you can go. And again, in Fahrenheit, it's negative 0.67. So these are all the same thing. 0 Kelvin, negative 273 degrees Celsius, and negative 459 degrees Fahrenheit. This is the lowest temperature you can go. So that's what we mean when we say getting close to absolute zero. All right. So as we increase our energy levels and we get a little bit warmer, we get into a solid. So we're going to be looking at water for the next 3 slides. But um, solids are something that have a definite shape, right? So if I picked up a glass, that glass is going to have a solid shape to it. Or if I picked up a pencil, that pencil has a definite shape, right? It's going to take up a certain amount of space, and it's going to stay that way um, until more energy is added. And it also has a definite volume, right? And it is not compressible. So if we look at this, if we look at these two representations, so this is the structure of ice, right? Ice, when we're talking about the atomic level, between all of these connections, all of these molecules in ice, these water molecules, there is very little space, right? And so it takes a lot of energy to compress a solid, right? To compress a solid, and even if you were able to compress a solid, the distance between these atoms would be really slight. It would probably deform and become something more liquid if you added more pressure to it before these molecules got any closer together. So it is not really compressible. If we add more energy to a solid, to our ice, and our ice melts, right, the phase transition between solid and liquid is melting, we know that liquid has no definite shape. So I can take the same cup of wine and put it in 2 different shapes of wine glasses, right? It just fills whatever container it's in. So it doesn't really have a shape that is definite and regular every single time. But it does have a definite volume. So a cup of water, no matter what glass it's in, is still a cup of water. It still takes up a certain amount of space. And again, these liquid molecules are they're still very close together. They're sliding, they have more freedom of movement. They're sliding past each other, right? There's a little bit of resistance. There's different flows in the liquid. But again, the distance between the molecules is still very slight, right? So even if you could compress a liquid, which has a little bit more space, but not very much more than a solid, you would push the atoms together slightly if you could compress the liquid. But for the most part, we say that a liquid is not compressible because the space between the atoms does not, it's really hard to make that any smaller. If we add more energy, we get our water hot and boiling, it is going to turn into a gas. It's going to vaporize, remember. And gases, like water, have no definite shape. So if I released a bunch of water vapor into a room, that water vapor is going to fly around, right? All of these molecules are very loose, and they're going to fly around each other. They are going to fill up the room that they're in. They're going to take the shape of whatever container they're in. But gases also don't have a definite volume, right? So the same amount of gas particles, because they're filling whatever container that they're in, they can be the same amount of gas particles can be in a small box, and the same amount of gas particles can be in a room, right? There's less space between the gas molecules in the small box versus the big room, but the same amount of gas can exist in both places. So there's not a set amount of space that the gas takes up. And because these gas molecules are floating around each other and there's a lot of space in between the molecules, we can compress it, right? We can compress gas and push those molecules. So we have our gas, right? And again, just to go back, Bose-Einstein is very, very cold, right? We're near absolute zero. And as we give more energy to our matter, we are getting into a solid, right? It has definite shape. All of the particles are very regular. You can see this crystal lattice of ice, right? This is what this might look like at a very small level. It's very regular, it's very uniform. The spacing is pretty similar, is the same all throughout, right? Remember that bent shape of water creates this specific kind of structure, right? Then, as we add more energy, we move water from a solid to a liquid, right? The molecules are moving past each other, they're flowing, there's the capacity for flows, and it doesn't have a definite shape. There's more movement, right? As the water has more energy into it. And at normal temperatures, like right now, it's about, 89 throughout the day. Water is just going to be liquid normally, unless, even if we put ice out, eventually the ice is going to melt and it's just going to be liquid at room temperature. Eventually, if you add more energy to it, like if we boiled the water, it's going to vaporize into a gas. There's going to be a lot of space between the molecules. They have a lot of energy. They're bouncing around. They're hitting walls. They're hitting each other. But there's a lot of space in between the gas, and it can fill up any container that it is in. And finally, we have plasma. So plasma is adding a ton of energy to gas. So if we look at this temperature or energy chart, low temperature or energy is on this side, high energy is on this side. So if we have a low, again, our low energy state of matter is solid, and here would be Bose-Einstein condensate. Then we have more energy, it becomes a liquid. We add a little bit more energy, it becomes a gas, they're free flowing. And then we add so much energy to our atoms, our gas atoms, that the electrons get ejected from the actual atom. So here, this is really extreme. It's like an explosion happening. But we have these ordered molecules. So nucleus, and then we have our electrons. You give enough energy, and the electrons in the nucleus just float apart from each other in this plasma gas cloud, right? And so that's what it is. There's so much energy that the atoms will literally eject an electron. And when we don't have electrons, then our nucleuses become our atoms are ions, right? They're positive ions because they don't have any negative charges anymore. They only have the positive charge of the proton. So we have our little positive ions, and then we have our electrons floating around in a little soup. And it's the most abundant form of matter in the universe, right? Like stars are made up of plasma. It's so much energy. This fusion reaction that's happening that creates stars is going to be the most abundant form of matter in the entire universe. Not necessarily on Earth, though. It's relatively rare here. We can think of lightning as another plasma. But it's really charged, right? So it has these positively charged particles, these atoms floating around, and then these negatively charged electrons just floating around each other, which means that it's going to respond to electricity, and it's going to respond to a magnetic field, right? And so if you think about the sun's solar flares, they don't just like spurt up like a fountain. They're kind of like getting whipped around in all these different really cool shapes. And that's because once you do have a plasma, it's going to accept charges, right? It's going to accept an electrical or magnetic field, and it's going to create flows, almost like a gas and a liquid, right? it's very much like a gas, but you're gonna create these flows, and charged particles are going to sort of connect to each other when there is an electrical field or when there is a magnetic field. And again, the nucleus is composed of the neutron and proton, and when you add enough energy, this gas will become ionized, right? These electrons will eject, and you have this floating soup of positive atom ions and these electrons floating around. And then once it cools down enough, we call it recombination. So some of the electrons will probably be lost, but the positive and negatively charged particles are going to recombine, and it'll become a gas again and eventually cool down to whatever state it goes into next. So I hope that y'all learned something. And if you have any questions, just shoot them my way. Bye.